E is a number just like pi, and it's very hard to explain because it's one of those irrational numbers that goes on forever and has like natural implications. So I'm gonna have a lady, super nice lady with an interesting accent explain to you what E is. And it has to do with, her video has to do with money. But you can see E in other applications than money. Money's the best one if you're, wanting to save money, which I should do more. I'm terrible with money. If you gave me a nickel right now, I'd figure out how to spend it somehow. How could you even spend a nickel these days? Yeah, like at one of those machines. I get some candy that would like rot my teeth. I don't know. But whatever it would be spent. Okay, here we go. Watching the video of the lady. I'm gonna stop it partway through, and I'm gonna appreciate it if you guys are not looking at other things while my video is going. That would be great. Hold on.
The base 10 and log to the base E. Why are they the most commonly used logarithms? How do we really understand them? Log to the
Sorry. 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 Sorry.
Understand them? Log to the base 10 is kind of intuitive. It's easy to talk in multiples of 10. 10, 100, 1000, and so on. Log to the base 10 gives us an easier scale to work with. Log 10 to the base 10 is 1. Log 100 to the base 10 is 2. 1000 to the base 10 is 3. And we can see that the multiples of 10 can be managed with a scale of natural numbers. But log to the base E is what I'm deeply interested in. It's called the natural log, and it's also written as ln. Yes, log to the base E is also written as ln. So log 20 to the base E can be written as ln of 20, the natural log of 20. What is this E? Some call it a magical number. Some call it an irrational constant. Some call it a Euler's number. But the harsh truth is this: very few people actually understand what E is. To get to E, we first need to understand growth. Let's say a particular thing doubles every time period. On this timeline, this is today, and every unit is one time period. Assume you have $1 with you. At the end of the first time period, this dollar doubles and you have $2.
No way.
At the end of the second period, $2 double to become $4.
No.
And at the end of the third period, we have $8. How do we look at this growth? First, we see that the numbers at the end of the time periods are powers of 2. It's in the form 2 to the power x, where x is a non-negative integer. 2 raised to 1, 2 raised to 2, 2 raised to 3, and so on. This was one way in which we looked at double growth. Another way to look at it is that there is 100% growth every time period. 1 plus 100% of 1 gives us 2. $1 was increased by 100% to get 2. In the second time period, $2 grew to $4. 2 plus 100% of 2 gives us 4, and so on. So doubling the value is the same as a 100% increase. So 2 raised to x can also be written as 1 plus 100% raised to x. It's like you're getting a 100% return on your investment. But hold on, we are making an assumption here. We are assuming that growth happens in a discontinuous fashion. We are seeing growth in steps here. What about the time in between two time periods? We are seeing no growth in between. No growth and it suddenly doubles. Again, no growth and suddenly doubles. But hey, that's not how nature functions. Everything or every kind of growth happens gradually. If your height today is 4 feet, you suddenly won't be 5 feet a year later. Your height gradually grows. When we started, we used to get around 30 views a day. And after a year, we started getting around 4,000 views a day. It doesn't mean our view count just jumped one fine day. It gradually increased. So growth in nature is never really discrete or discontinuous. Let's see how it really works. We take the example of $1 growing over 1 year at a 100% growth rate. First, we look at the annual growth. Based on what we saw, at time 0, we would have $1. And at the end of the year, we will have $2. This doesn't seem right because all the interest cannot appear on the last day. To make it slightly better, let's divide the year into 2 equal parts, 6 months and 6 months. Splitting that 100%, the growth would be 50% in the first year and 50% in the second. It would look like this. Our initial dollar earned 50% interest in the first half to give 50 cents more. Now what happens in the second half? $1.50 remains as is. The growth is 50%. So 50% of $1 will be 50 cents. And this time, the 50 cents also earned a 50% interest. That will be 25 cents. This 1.5 is the sum of our original dollar and the 50 cents we made here. So at the end of the first year, we have our original dollar, then we have the dollar that made our original dollar made, and we also have the 25 cents that these 50 cents made. A total of $2.25. This is better than doubling. If we want to understand this using a formula, it would be 1 plus 100% over 2, the whole squared. We had half the growth rate over 2 time periods. This is also referred to as semi-annual growth. Let's push ourselves further. What if we had 4 equal time periods in a year? We have divided 1 year into 4 quarters. This is how it would look. Looks messy, but it's actually very simple if you've understood the concept. It's 25% growth every quarter. The formula would change to 1 plus 100% over 4, the whole raised to 4.
Okay. Let's talk about this mess of money that you would make if you were somebody who saved money. Unfortunately, this would apply to Mrs. Talmadge. She would have a very cheap Squishmallow from a thrift store or something. But anyway, if you were someone who was responsible with money, this is how it would look. Okay, there's your original dollar in the bank, right? Okay, everybody okay with that? Okay, now after 3 months, you would have your original dollar still in the bank because you resisted the urge to take it out and buy a Squishmallow, and your dollar would have made you 25 cents. Interest. You guys know what interest is? So interest is money that the bank gives you in exchange for using your money. So when people, you ever wonder how like a bank gives a really big loan to somebody? They use it by using your money. I know, and that's one of the reasons that the stock market crashed, because they were loaning out too much of other people's money and they didn't have enough money to like pay those people back. And that's why if you have a bank now, you see what's called FDIC insured at the bottom. That means that the government will bail that bank out or whatever that is if they have bad business practices. Okay. You know, little finance lesson from the day from the lady who buys gumballs. Okay, now this is 6 months. This $1.25 from the 3 months would go here. Then your dollar would make another 25 cents, and this 25 cents would make 6.3 cents. And then why it's called compounding interest is because it means that it all squishes up and then you have that money stored that compounds into one thing. Okay, here we would have all of this added up, and then this $1.25 would make you 31 cents. And that 25 cents would make you 6 cents, and then that 6 cents would make you 2 cents. This is why saving money is great. You should definitely do it. Except for that, I can't do it. Anyone else willing to say they have no money willpower?
We would approximately get $2.441 at the end of the first year. I suggest you pause the video and understand the quarterly growth diagram really well. The 100% is nothing but 1. If 2 time periods, then we have 2 here. If 4 time periods, then 4 here. So the formula for n time periods would be 1 plus 1 over n, the whole raised to n. Clearly, more the number of time periods, higher will be the returns. This will give us the dollar value at the end. I probably know what your greedy brain is thinking. Is it possible to get unlimited money? Let's make a table now. Number of time periods and the dollar value in the end. If it's just 1 time period, the dollar value is 2. If 2 time periods, then $2.25. If 4 time periods, then $2.44. If I divide the year into 12 equal time periods, my return will be higher than this. If I divide it into 365 equal time periods, it will be even higher. This tells us that $1 at the start of the year will become these many dollars at the end of 1 year if the number of time periods is 365. So if we increase this number significantly, that is, if we increase the number of time periods significantly, will this number also increase significantly? Okay, here are a few more calculations. The number of time periods here is 1 million. Notice that the returns improve, yes, but they converge around a value which approximately equals 2.718. And that is your beloved E. We can't get infinite money after all. What would be a layman-friendly explanation for E then? It is the maximum possible result after continuously compounding a 100% growth over 1 time period. Yes, that's E. Don't forget, we had assumed a 100% growth here. And that's what E is. It's the maximum we get after a 100% continuous compounding growth over 1 time period. Notice what compounding does. The first result is 100% without compounding. $1 would become $2. But after continuous compounding, $1 will become $2.718 approximately. That would be a growth rate of 171.8%. That's like the maximum growth we can have. So E is approximately 2.718. It's an irrational number, which means the digits after the decimal point do not repeat and go on forever. Just one last question. What if the growth rate and the time period change? Will E still help us? Absolutely. There's no problem at all. In general, the growth after continuous compounding is given to us as e to the power r times t, where r is the rate and t is the number of time periods. So if we have a 200% growth for 5 years, then it would be defined as e to the power 2 times 5. We squared e to include 200% growth and we raised it to 5 as there are 5 time periods. It'll give us e to the power 10. E is nothing but the maximum possible result after continuously compounding a 100% growth over 1 time period.
Wasn't that fun? Oh, no. What?
What you do, right, is put that dollar in, so your parents put it in when you're born, right? And then the it's just 5 days, and then you get whatever it comes out to, right? But then you take all that, you put it back in. And so over time, it gets more money, keeps increases out even more.
That's a great idea, except for that I have Squishmallows now and no money. Where was Will French? Okay, so she actually in the video gave us 2 formulas. She gave us a formula for time periods and she gave us a formula for continuously. Come down, guys. Come down here like a couple of lines because we're gonna make some arrows to our formulas to say what the things are. Okay, so this is the first formula she gave us. She didn't give us the whole thing. And I changed mine to have variables so I can change it up because I don't want to use 100% every time. But let's define what all of these letters are with some arrows. So A is the new amount. So A stands for amount, and that's the new amount. P stands for principal, not the really nice lady downstairs, but principal in banking terms means the initial amount. Now, in the video, she didn't have P, and that's because she was starting with $1 every time. So that P was 1, but she just didn't write it there. Okay, this is actually a 1. This is the rate as a decimal. In the video, hers was also 1 there, and that's because she was going with 100% growth each time. N is the number of time periods, like she was saying, but we're going to say number of times compounded per year. So when she did the quarterly one, that would be a 4. When she did the monthly one, that would be a 12. And then T is time in years. These problems are my favorite problems because all you have to do is plug the numbers in and then hit enter on the calculator and it is over. Also, because they're actually useful. This is how you can figure out how to save money. Okay, now continuously, that was what E was for. And the formula for that is A equals, and we will officially refer to it as PERT. PERT is PE to the RT. PERT. A is still the new amount. P is still the principal. E is actually a number, which is approximately 2.718 from the video. R is the rate as a decimal. And T is time in years. Okay, before we do our example, I'd like you to find the E on your calculator. And it actually, E is the inverse of natural log. She was talking about that at the beginning. After we do our one example, we're going to do E and natural log problems, which is why we had you guys doing logs a couple months ago to bring it back. Okay, so find your calculator. And E is located above the natural log. Okay, so regular log is next to the 7, and the inverse of regular log is 10 to the. And then natural log is next to the 4, and the inverse is e to the. Okay, now notice this is e to the x. If you guys could actually type it, so go second natural log. It's going to blink there because it wants you to put an exponent in every time. If you're looking for just plain e, just do e to the 1. 2 points, so lots of stuff. Okay. All right, so we're going to do one example. These are favorite problems. They're super easy. And then we're going to work on logs, which is in your packet. Ms. Rice and I despised the CPM number 179, so we made our own. Now, I have to tell you, I don't think any banks compound continuously. My stepson, my oldest stepson, is an accountant, and he says that Poppy Bank is the bank that gives the best returns. And he has a lot of research into it, so if you're looking for an investment, look up the interest rate for Poppy Bank. My youngest stepson, he has a problem just like Mrs. Talbot. He's not related to me, but somehow he got my money managing habits. He's got 3 watches, about 14 things glued to his car, aftermarket things. He's got 3 tattoos, but he doesn't have anything. So his graduation gift is going to be a certificate of deposit investment that is going to be in there for a few years. And the reason that we were looking at interest rates was to get him the best interest rate for that, which I'm thinking is Poppy Bank right now. But anyway. Okay, all right, so we're gonna do quarterly over here. So quarterly means time periods. And then continuously over here. Okay, so I'm gonna scroll up just a little so I can see my formula. Okay, so here, quarterly, A equals, okay, the principal is the initial amount that you put in, which is $10,000. Yeah, right. Parenthesis, this is just a 1 plus. Okay, and then R is a rate as a decimal. So what I mean by that is you have to take the 3% and put 0.03. So you move the decimal over 2 spots to make it a decimal. And then number of times compounded per year is 4 if it's quarterly. Does that make sense? Because it's broken into 4 quarters. Okay, and then N is also here, so that number is also here, and then 10 years. Okay, so just plug this guy in. 10,000, parenthesis, 1 plus 0.03 divided by 4, end parenthesis, to the 4 times 10. 13,000, that's nice. $13,483. And then whenever, this is the most important thing I'm going to tell you, I don't care about any of the rest of the math stuff I've told you this year. If you're doing a problem with money in it, round to the penny, which is 2 decimal places. Benicia High School needs to graduate children who understand that money is a real thing. It is not just a transaction based on a debit card. That are actually real coins and things. Although I did hear a rumor that they're going to stop making the penny.
Whoa.
It's not a rumor. Huh. So are all of my super old, gross, and dirty pennies going to be worth more than a penny? Okay, so what I mean by my little lecture is round to the penny, which is 2 decimal places. That way you look educated in finances. Yeah. I have stats students, love them all, bless their hearts, but they will put like 13,483.5. I'm like, I'm gonna get you a job at a store where you have to run the cash register. Okay. Now continuously looks a little bit different. It's called PERT. A equals, the principal is still $10,000. That's not a parenthesis. I don't need a parenthesis. I don't know why I put 1. It's completely unnecessary. Okay, And then E is actually a number. It's 2.718 something. R is still 0.03. And time is 10. Does that make sense, guys? Okay, so then 10,000. Practice doing this because it's the first time probably you've used the E. Go second natural log. And then in the exponent, do 0.03 times 10. And you get more money. Okay, so I think as she was saying, the more times a bank compounds your money, the more money you get. That's because whatever interest you gained is now yours, basically in your bank account. And as that grows, then your interest grows. Um, again, I've been looking at bank stuff, I mean, for other people. And I don't think I've seen any that do continuously compounding. They're stingy. They don't want to give you the money. Okay, now go in your packet, guys, and find number 179. It's a very algebra looking page, like it's not fun about money, it's just regular old problems. He's okay. I know Chris is gonna need this too he's needed this for his online pre-calc.
That's what I'm gonna,
Are you?
I'm sorry. You're late. Thank you.
Poor Sam. Guys, okay, so, these are natural log and E problems. And the good news is they keep the log the same rule, almost all the same rules as regular logs. So I'm gonna talk you through this, with the same sort of style that we did from chapter 7. Okay, number 1. First thing I need you to know is that this stands for natural log. That is not an I. Please don't say IN, that is LN. The reason that L comes first is because the calculator menu is in alphabetical order. They wanted you to see regular log and natural log, so they put the log first. So it's log natural. Even though we don't say log natural, we say natural log. Anyway, okay. The first thing you do is look at the operation and notice that it's subtraction. Subtraction for logs is division. Nice. It's still in there, guys. Okay. So natural log 4 over 5x equals natural log of 2. So that's called condensing a logarithm. You condensed 2 logarithms into 1 logarithm. It doesn't matter that it's natural log. Same process. Okay, now you say to yourself, is it Guinan circle or cross out? Guinan circle or cross out? Yeah. Okay, now when you get a problem like this, I like to put that side over 1 and cross multiply. So like this. So 5x times 2 is 10x. 4 times 1 is 4. Divide by 10. X equals 0.4. Okay, now all of the log ones need to be checked, just like all of the old log ones. Grab your calculator, type natural log of 4 minus natural log of 5 times 0.4 because we're plugging in, right? You guys see what I'm doing? And then you're going to get a weird answer. That's because it should match natural log of 2, which is on the other side of the equals. Haha. Okay. We're gonna do 4 of them together, and then I'm gonna have you do 4 in your groups. So we're gonna move on to number 4 next. Okay. Everybody okay with number 1? Okay, number 4. I look at the operation, and this one's kind of confusing. This is actually negative 2x. It would be better if that was in parentheses. The operation is plus. Okay. In logs, plus is times. Yep, great job. Natural log negative 2x times 2 equals 3. Natural log negative 4x equals 3. Okay. Now that's all the old stuff. That's not true. You should see that it's Guinan circle. Everybody see that it's Guinan circle. Because it's a number on the other side, not a log. Okay. When we do Guinan circle, you need a base to start your circle, right? Okay, so what you're going to do is you're going to take your natural log and you're going to rewrite it as log base e. And then do your Guinan circle. Natural log is log base e. E to the 3 equals negative 4x. Okay, practice doing the e on the calculator. E to the 3 divided by negative 4. Okay, now wait. Directions say 10,000. This one was the decimal came out evenly. This one does not, so we do 4 decimal places for log. So 0, 2, 1, 4 equals x. Okay, now let's plug it back in. Natural log negative 2 times, and I'm going to scroll up and grab that because I'm too lazy. Plus natural log of 2. Yep. 3 equals 3, check. Okay. You guys ready? Okay, number 5. These are the opposite. These are squirrel in the tree problems. But they follow the same rules as regular squirrel in the tree problems. Add 1 to both sides. Okay. Now we did log problems recently in your theory stuff. What do we do to get a squirrel out of the tree? Yep, hit it with a log on both sides. Okay, the exponent's gonna go in front and protect it with parentheses. However, pause here. When you have an e in the problem, you don't just regular log of both sides. You natural log both sides. Okay, and why is that? Well, the reason is because natural log and e are inverses of each other. They cancel out. So if you wanted to play with that, natural log of e to the 1 is 1. Natural log and e are inverses of each other. They cancel each other out. What do you think natural log of E squared is? 2. Okay, anyway, n plus 2 equals natural log of 10 minus 2 natural log of 10 minus 2 0.3026. And these problems you don't need to check. You only need to check when it's a log problem to start with. Because exponents can be anything. It's just logs that can't be anything. Everything. Okay. Number 7, last one we're going to do together. Then what I'm going to do is dig through my folder and find the answers for these 4. I'm going to put the answers up so you can check them because you're going to do them in your groups. Okay. Number 7, last one. Add 8.2. Negative 86.8. Divide by negative 8 on both sides. Oh no. Leverage issue with the camera. Okay. Now I'm at the spot where I can log both sides, but I need to make sure I natural log both sides because there's an E in the problem. The V minus 3 is going to go in the front, protect it with parentheses. Natural log of E equals natural log of 10.85. Natural log and E cancel. Add 3 to both sides. And be careful when you're doing the calculator. You see how I end my parentheses? You have to do the same in the calculator. 5.3842. Okay, you guys, I want you guys to try the other 4. I'm going to dig through my file and find the answers to the other 4. And I'm going to write them up there so you can check your work as you go. Do not write just the answers down, please, and thank you. Excuse me.
negative 2.70. That's what I was gonna do. Don't crash.
No.
Be that. That would be, that's well.